Hello, everybody, and welcome to our webcast. This time, a bit of a knowledge webcast. Today, we're talking a bit about infrared, a world beyond the visible. Today's agenda is I will give, as usual, a brief introduction about Laser 2000, and then give an overview about basics, applications, and technologies, especially for the infrared. In the end, we'll have a Q&A session where you can send us your questions using the chat function in the control panel. Please, whenever you have a question, please feel free to use it right away and during the entire webcast. And in the end, we will try to cover all of your questions. If a question may be a bit too special or needs a longer explanation, we will get back to you via email and answer your questions then. Laser 2000 has more than 35 years of experience in all facets of photonics. We work with manufacturers all over the world to provide their innovative products to our local customers. We have contacts in Germany, France, the Iberian Peninsula, and Scandinavia. We have also Laser 2000 branded partner companies in the UK and Benelux. With our passionate experts and our wide portfolio, we can provide comprehensive solutions for every project, no matter how special. When I said portfolio, as you can see, we have nearly everything in the fields of photonics. So we provide laser and light sources, stuff for laser material processing, of course, laser safety, and everything around today's topic, the infrared region. But now let's start. Infrared, what is it? So in the infrared range, we're talking about the spectrum of electromagnetic light, which is longer than the visible wavelength range. So when we're talking about infrared, we're talking about wavelengths longer than visible light, but frequency and energy are below frequency and energy of the visible and of the red light. Often, infrared is described or confused with heat radiation. So if you take it precisely, nearly all types of electromagnetic radiation can cause temperature increase in material. It only depends on the absorption spectrum of the regarding material. And you can find infrared nearly everywhere, but I will show some examples of that later. So infrared is categorized in many confusing ways. So in this table here, we'll show categorization according to ISO and DIN or CIE, where we have, which is divided in near infrared, medium infrared, and far infrared, or infrared A, B, or C. As you can see, infrared A and infrared B are pretty close to each other and only divided by a big absorption band of water. This kind of grew historically. In the English-speaking regions, there's also another division of the ranges, which is NIR for the IRA region and SWIR, so shortwave infrared, for the IRB region. Sometimes it's everything is depending on which product or what you're talking about. It's used the same way. Then in the medium infrared range, this is divided by mid-wave infrared and long-wave infrared and has a bit of a different different division in terms of wavelengths. And then we have, again, the far infrared, which is starting a bit earlier than in the ESO declarations. But now, where can I find it? You can find infrared in nearly every, let's say, electronic or electric device today that you're using. It may be your mobile phone having face recognition or proximity sensors. Face recognition, of course, to conveniently unlock your screen, proximity sensors to shut off the screen when you're putting it on your ear, to have a phone call. You'll find it in the remote control in most devices. Motion sensors for automatic lighting are recognizing infrared radiation given out by, let's say, the human or a living body. And even in things like CD players, where you have like red or in some cases near infrared laser sources to read out the data or music from the CD. But of course, that's not everything. Now that we know where we can find it in some cases, how can we detect it? As in the visible range with normal cameras, spectrometers, photodiodes, there are also solutions for the infrared range, ranging from single element detectors like photodiodes, avalanche photodiodes, linear camera arrays, matrix camera arrays, and also like indirect detectors like conversion screens, converter crystals, sensor cards. What you can use depends always on your application and on your needs. In terms of electric sensors like used in cameras and photodiodes, these often consist of semiconductor materials in the 3.5, 4.6, or 2.6 semiconductor range, because they have a suitable band gap to detect infrared light. And of course, we need something that we want to detect, despite of that oftenly confused heat radiation. Infrared radiation, as said, you will find a lot of sources also right where you look at it. It can start from simple sunlight. You can have incandescent light like halogen lights and so on, infrared LED lighting, VCSELs, laser diodes, solid-state lasers, and of course, ceramic heat emitters or even the human body. Depending on which infrared range you use, even cosmic background radiation will do the job of illuminating. But when we go down to 3 Kelvin, we are starting to talk about like terahertz or microwaves. One point of application where you can use infrared light is infrared spectroscopy. Infrared spectroscopy gives more or less directly molecular information. Typically, we have interaction of light when we're talking about spectroscopy, interaction of light with matter, and the absorption, especially of infrared light, leads to energy transfer, causing the molecules to investigate, to change their molecular states, rotational or vibrational states. There are two regions we're looking at. So infrared spectroscopy is always or nearly always talking about wave numbers, which is kind of a inverse scale for wavelength, but it's directly proportionate to energy. Typically 400 to 4,000 wave numbers, that equals 25 micrometers to 2.5 microns. You can find fundamental vibrations of chemical functional groups, like shown in the picture beside me. And then there's the near infrared with wave numbers bigger, 4,000 wave numbers, and wavelengths smaller, 2.5 microns. which mainly consists of combinations and overtones. Typical measurement setups can be in absorption, transmission, or reflection matter, but you can also measure emissions like emission of a halogen lamp or radiography of the sun or everything else. Determine the wavelength of your laser. For the, let's say, mid-infrared or fundamental infrared spectrometers, today most used form is the Fourier transform infrared. It's very cost efficient, high accuracy measurements, and pretty fast in comparison with like scanning systems that you used like 20, 30 years ago very, very often. So they're available as small tabletop units, just 30 by 30 by 30 centimeters, and they have a high variability. You can also have additional additional accessories to perform like Raman and other infrared measurement techniques. Rather new development is MEMS technology. So the entire interferometer part of such a spectrometer can be miniaturized to the size of like the palm of your hand, or even or even smaller. So you can get things like this flashlight looking spectrometers for measurements in the infrared and in the near infrared. In contrast to these Fourier transform infrared spectrometers, near-infrared spectrometers work mostly dispersive, which means you can get a spectrum at one shot, and they can be used in a modular way, and they are, especially when you have this one-shot functionality, you can do like kinetic measurements, so you can look at changing samples over time, which is a bit more complicating working with Fourier transform units. Infrared spectroscopy is very often used in typical lab application, like in chemistry labs, in the chemical industry, in the pharmaceutical industry, especially to find out, what's the material we are looking at. Near-infrared spectrometers can be, because of their modular shape, used like nearly everywhere where you want to put it. You can use it in astronomy to see molecules develop in an early stage when planets form. You can use it in agriculture, as seen on the lower right, for like online assessment of your fertilizer, of the ground state, and so on, and so precisely dose the chemicals on your field, and so prevent costs, especially now when the fertilizer prices are exploding. Of course, for medical examination, like blood investigation and so on, but also food and recycling applications. The next step, coming from the kind of one-dimensional sensor for spectroscopy, would be take it to kind of a 2D image, which leads us to infrared imaging. As already mentioned, there are several different regions in the IR, with the NIR and shortwave IR, which are nearly directly adjacent to the red end of the visible spectrum. Typically, it's used for reflective measurements or reflective imagings. This is due because there's nearly no thermal emissions at lower temperatures, but it, as used in NIR spectroscopy, you can also use it for chemical imaging with the right filters or moisture detection. The mid-wave and long-wave infrared are typical, where you can image, where you can see the emission of things. You can do like thermal imaging at elevated or room temperature or even lower. And you can also see chemical imaging or gas detection. And in the long wave IR, especially thermography is one of the examples. So looking at the near infrared and shortwave infrared, in the infrared light, it shows less interaction with matter in comparison with the visible light. And therefore, it has a higher penetration depth and less reflections on surfaces. What you can see here on the right side, especially, is the comparison between the visible visible inspection of a bonded wafer and in the infrared, where you can see on the one hand less reflection of the table here, and on the other hand you see there's a transmission and there seem to be some voids in that wafer. This is because silicon becomes transparent after like 1200 nanometers. But also other semiconductor materials can be inspected that way. Another point can be colored materials. For many applications, the colors can be penetrated by infrared light, and you can directly take a look at on the inside or on lower layers of your product. Another point, as mentioned, high temperature thermal inspection. And as you can see here, we have two glasses here. And this one, the right one, is about 300 degrees Celsius, and the other one is room temperature. You barely see it. And there's one of the big advantages of shortwave near infrared. You can see through glass. And of course, as a lot of high power lasers are working in the shortwave infrared field, laser monitoring can be performed using such cameras. In the mid-wave, long-wave infrared, there's a strong use in thermal and thermographic inspection in production environments for electric circuits and mechanical systems to see where failures may occur. Like here, having a hot part and a cold part, and here the pipes that are adjoined. The one is rather cool, the other one is rather hot. So it's possible that there may be some kind of distortion in the process or some kind of failure seems to foreshadow here. Then in the mid-wave infrared especially, you can do something like remote gas and leak detection, as here in the pseudo color image, where you can see some clouds of methane above the sea. And of course, things like security and surveillance, just as an example for long wave and thermography. Another point, and this is pretty interesting because it's a combination of the imaging and the spectroscopy part, is the multi and hyperspectral imaging. It's kind of an imaging spectroscopy where you create three-dimensional data with 1D or 2D sensors. There are several techniques that you can use. There are techniques like push broom cameras, where you scan your image line by line and get for each pixel in every line and get the full spectrum depending on your sensor. You can do spectral scanning, like in a staring manner, where you can tune some kind of optical filter before your camera and just take a video and see how your image changes when you change the wavelength, the passing wavelength of your filter. There are snapshot solutions where you take a huge image, which consists of many smaller images that are divided by wavelength, and other techniques like spatial-spectral scanning or spectral mapping. The whisk broom technique, which is mostly used with typical point spectrometers, where you just go on a pattern over your sample and then create an image out of the peaks of the spectrum. For multispectral imaging or hyperspectral, there are a lot of applications. Here already again to mention is precision agriculture, because a lot of indices contributing to plant health can be assessed by infrared hyperspectral imaging. You can monitor the environment, then stuff like food inspection, where you can see with infrared, just see beyond the peel of the apples and find some bruises. In this image on the top, you will see the apples. They look nice and juicy, but when you look in the near infrared image, there are some points highlighted, and when you peel these apples, you can see there are already damages in the exocarp or in the flesh. Of course, sorting applications and material identifications are perfect examples for it as well, like having here a lot of white pills, and when you can see in the trained and classified pictures that they are not the same, as you can see also from the spectrum below there. Another technique used in biosciences, for example, is multiphoton microscopy. So as you may know, so when you use microscopy, in the visible range, you can barely look beyond the surface, but this is due because the visible light has a rather low penetration depth. And in biosciences, if you want to distinguish different cell types or something, you like to stain them with a dye and maybe highlight them with fluorescence. But typically, this fluorescence occurs in the visible, and excitation of fluorescence dyes typically occurs when you excite them with a shorter wavelength. But when you go deeper, you need to work with a small tweak. When you use an infrared source with a high photon flux, like a short pulsed, like femtosecond laser, you can take the advantage of the infrared and gain high penetration depth. And when you have the high photon flux, the possibility that two photons arrive at the same time at the dye molecule will push it up into an excited state, and when it relaxes, it will then fluoresce in their color. Another advantage is that in these cases, excitation and the fluorescent signal are so far apart from each other that they are easy to separate, and you maybe do not even have to use expensive filters in that case. Another big field when working in the infrared light are a product field are VCSELs. There are a lot of VCSELs emitting in the infrared range around 900 nanometers. They can be used for invisible illumination, especially when you go in traffic. You don't want to blind each other. So as the human eye is blind right after 780 nanometers, you can use this pretty good. And this is very helpful when using like autonomous driving assistance systems and so on. As mentioned before, proximity sensors and stuff like that used in electronic devices like tablets and smartphones and so on can also use like these small VCSEL units and measure the distance in a time of flight matter to see when you put the phone near your ear. Another example can also be like these robots working through themselves through warehouses, but of course they shouldn't run over human workers, so they need to avoid collisions in any they just need to avoid collisions with humans, with other robots, and so on. Points like structured light for 3D face mapping and the facial recognition to unlock maybe your phone screen are another application where you can use VCSELs in the infrared range. As I already mentioned, the photon energy of the infrared light is lower than in the visible. So one may tend to be a bit less careful when using infrared. But infrared radiation just poses some dangers for the user, especially eyes and skin, because you won't directly see or feel a interaction with the human body tissue. When we take a look safety considerations for the eye, the infrared A region below 1400 nanometers is the most dangerous for the human eye. As it's a bit more shortwave, and it's below the intensive water absorption band in the infrared. It can penetrate through the cornea, the lens, and the vitreous humor, and reach the retina. But as you don't have an infrared receptor in your eye, the eye won't or cannot use any protection reflexes directly. So you don't have any optical induced corneal reflex, which would lead to close your eyelid, as you may have it with blinding some light. And you will also have no pupillary response, which just lowers the incident amount of light. And another point is high power lasers are very common in the spectrum range. Just thinking of neodymium YAG and ytterbium YAG lasers, which emit right above 1000 nanometers. In the longer wavelength regions like IRB and IRC, most of this radiation is absorbed by water molecules on the surface of the human eye. So, nevertheless, high energies, of course, can destroy tissue and then give acute symptoms. But also a long-term exposure can lead to things like a cataract and may often occur after a longer exposure period. Of course, a bit of the same issue here for the skin. The infrared A light can penetrate the epidermis and the dermis, and this means the light will be absorbed and the energy will be exchanged in deeper layers, which reduces the perception of heat, as the receptors for heat are more in the top layers of the skin. So a deeper laying tissue damage may not be noticed first, and a longer exposure can also lead to effects ranging from accelerated skin aging, dry skin, and it may lead out to skin cancer. So make sure you be careful there. As IRB and IRC will interact also with the upper layers of the skin, you may notice a local heating where the light impacts the skin. But nevertheless, long-term exposure can lead to erythema, so like your face or your skin is blushing red, or other skin alterations. And of course, high energy impacts can lead to burns and destruction of tissue. So that's it just for now for the presentation. And we would like to start with the Q&A session now. So please just continue sending questions to us, and then we'll try to answer them right here in the webcast. That's right, suitable to the last topic we had here, literature recommendations regarding safety regulations. Yes and no. Yes and no at this point, because it always depends where on Earth you're located. So for the German or German-speaking regions, I can just give a list of some literature, but you can also reach out to our experts from the Light and Laser Safety Department, and they are happy to provide you with any information regarding coherent or incoherent infrared light sources. What about fiber optics and telecom? fiber optics and telecom is a very wide field. Of course, they are dealing very much in the infrared range. For these topics, we have a extra division or an extra team that can provide you with information on your needs for fiber optics and telecommunication. And yes, just reach out to me and I'm happy to connect you with them. So for now, all I can say to you is thank you for your attention. And if you have questions or any topic dealing with infrared or any other topic of photonics, feel free to reach out to me. And then you will get your answer, either from me or when we have another specialist for your topic. We are happy to provide you with information, answers, and solutions. So then take care and goodbye.